sharing my screen. Can you see my screen?
Yes, please.
All right. So what we'll do is we will finish some concepts related to what is called as independence, and then I'll take the audience through a simple example of what is called as probabilistic modeling. Okay. Now, let's understand the idea of independence. Okay, let me give an example, and let's see what your intuition seems to suggest. You toss a coin, you get a head or tail. You toss the coin again, you would again get a head or tail. Would the result of the second toss, would it be impacted by the result of the first toss? What does your intuition suggest? No, that's right. You don't expect that to happen, right? Now let us say you toss the coin, and then somebody is not on mute. Wait, who's that? Can you go on mute, please? Thank you. Right. So let's say you toss the coin, and then it falls, say, in a muddy place, such that when it falls, some mud gets stuck to one side of the coin. Now you don't clean the coin, you just retain the way it is, and then you toss the coin again. Do you think there is a possibility of the result of the second toss being impacted by the result of the first?
Yes, please.
There is a possibility, right? So now we understand this idea of intuition, I mean, the idea of independence intuitively, but we need a formal definition as to what exactly independence is. Okay, so let's define that formally. So we say two events are said to be independent if knowledge that one occurred does not change the probability that the other occurred. All right. So always remember, the idea of independence is for a set of events. It's never ever for a single event, because it doesn't make any sense. You can't say A is independent. It doesn't mean anything. You can say A and B are independent. A, B, C are independent. A, B, C, D are independent. Right? So it's always for a set of events. It's never for an individual event. So if you look at this, the second point, it says A is independent of B if probability of A given B is equal to probability of A, which means given B, if I'm trying to calculate probability of A, well, it's not going to alter anything. I'll exactly get the probability of A as though I didn't know B had occurred. So the information of the occurrence of B, even B, does not impact the probability of A. All right. And here's a formal definition. It's simple. Probability of AB, which means A intersection B, is equal to probability of A into probability of B. It's as simple as that, which means we're saying, look, there's an event A, there's an event B. And if you want to figure out the probability that both A and B has occurred, it's simply the probability of A multiplied by probability of B. All right. Now I have something there. This also means probability of A given B is equal to probability of A, and probability of B given A is equal to probability of B. Why? Can you help me deriving this? Shouldn't be too difficult. Anyone? Given this expression, the one on top.
The formula for probability of B given A will be probability of B intersection A. So considering that A and B are independent, that will be expanded as P of A into P of B.
Okay.
divided
cancels.
by P of
That's,
A. So P of
that's
A, P
right.
of A cancels.
Right. So likewise, you do the same logic for the other one too, right? Perfect. So what Madhumita said was, if you take probability of B given A, we know that's nothing but probability of BA. So when I use the word, I'm sorry, when I use the phrase say BA, I mean B intersection A divided by probability of A. But we also know probability of BA is probability of B into probability of A. So, you know, stuff cancel out and you get uh, this expression. And it's easy, you can figure it out. Okay. Here's a simple problem. I don't want you to solve it, but the technique to solve it would be simple. Here are two events, H1 and A. So if there's ever a question that's posed, which where you're being asked, are H1 and A independent? All that you have to do is calculate probability of H1, probability of A, and probability of H1A, and see whether the probability of H1A is equal to probability of H1 multiplied by probability of A. That's it. If you're able to establish that relationship, basically you're trying to figure out, look, there's probability of AB, you figure out probability of A, you figure out probability of B. If probability of AB is equal to probability of A into probability of B, we say A and B are independent. So likewise here, figure out the probability of H1, probability of A, then figure out the probability of H1A, and then see whether probability of H1A is equal to probability of H1 multiplied by probability of A. All right, trivial stuff. I don't want to bother you with that. You can solve this when you have the time. Now let me establish how we figure out independence when you have more than two events. All right. So if there are three events, ABC, then all of them should hold good. Okay. Or if we say ABC are independent, then all of them will hold good or should hold good, which means you take them pairwise, two at a time. This relationship should hold good. AB should be A into B, BC should be B into C, AC should be A into C. And you take three at a time, ABC, then probability of ABC should be probability of A into probability of B into probability of C. All right. Can somebody take a guess using similar arguments, the one that I just talked about a short while ago? If there are n events, A1, A2, all the way up to AN, what are the conditions that should be satisfied to say that they're independent? Or let's put it in a different way. I'm saying A1, A2, all the way up to AN are independent. If they are, what conditions would be satisfied? What is your take? Don't get into the specifics, folks, because a lot of events here, but argue it the way we argued for ABC. I want to hear your arguments. What did we do here? We took two at a time, and then we took three, right? Can you pursue that argument here again? Just pursue the same argument. Give it a shot.
The probability of intersection of any two events will be the multiplication
Okay.
of the
Number
individual
one,
probabilities.
next. That's one. Then, is that all? If you look at the first piece, ABC, did it stop there? I took two events, and then look at the last. Look at this.
Then the probability of intersection of all the events will be the
Okay. Okay.
multiplication of
It's
probability of
actually a
individual
little bit
events.
more nuanced. What you need to do is, you're right, probability of, you pick two, and then if you take A1, A2, it should be probability of A1 multiplied by probability of A2. Then what you do is you take three at a time. A1, A2, A3, A2, A3, A4. And then that will be A1 into A2 into A3. Then you take 4 at a time, 5 at a time, 6 at a time, and then finally all n at a time. That's the basic idea. All right. Okay.
Okay.
I'm not going to derive all this because our objective here is not to do a lot of derivations. Okay. So I don't want to bore you with derivations, but just understand it's extremely, extremely important because in many circumstances, we assume that uh, events are independent. Most importantly, you would assume that they are conditionally independent. Let me explain what that is. We say events A and B are said to be conditionally independent given E. Okay, events A and B are said to be conditionally independent given E if P of AB, which means P of A intersection B given E, is equal to P of A given E multiplied by P of B given E. All right, that's given E, you calculate probability of AB, that's LHS. And then in the RHS, you have probability of A given E multiplied by probability of B given E. So in a way, it's like a basic definition of probability where P of AB is equal to P of A into P of B. It's just that you put a conditionality here. That is given E, given the knowledge of E, you calculate probability of AB. And if it's conditionally independent on E, then P of AB given E is P of A given E multiplied by P of B given E. Okay, that's conditional independence. Now what we'll do now is we'll stop here and we'll go to an example. We'll do some probability modeling. Okay, this is sufficient for us. So what we're going to do now is what is called as probability modeling. And here is an interesting example that you've already worked with. Again, the tennis example, right? Now you must be wondering, this keeps coming up again and again. I think, is Sirisha here? She isn't, right? I don't think she joined today. All right, so which means everybody knows Tamil. விடாத கருப்பு மாதிரி இது வந்துகிட்டே இருக்கும். All right, but it's fun. It's very interesting because you get to know how the same problem is tackled using different approaches. So we tackled this problem using decision tree. We tried ID3, we tried C4.5. Now we'll do something entirely different. This is called as probabilistic modeling. Okay, so let's give it a shot. So we'll also try the assumptions that go, that go into probabilistic modeling as well. Okay, so the usual tennis set: outlook, temperature, humidity, windy, play. So many times you've seen this, you must have got bored. So I'm not going to explain that data set anymore. The question is, can we build a probabilistic model using this example and predict the target variable? Here, what's the target variable? Everybody knows it's play. I'm not going to explain. Yes, we can. So what we're going to do is we're going to take a particular row. I'm throwing this values for outlook, temperature, humidity, windy. Okay. So I'm saying outlook is sunny, temperature is cool, humidity is high, windy is true. If these features take the following value, what is play? How do I classify this data? Should play be yes, or should play be no? That's the question, right? Now we call this outlook is equal to sunny, temperature is equal to cool, humidity is equal to high, windy is equal to true as evidence E. All right, it's evidence because this is what you see. These are the features that you see. Call that as evidence or data, with whatever way you want to look at it. Okay, I'm calling it evidence. Now What are we trying to figure out here? We're trying to figure out the following. Give me a moment. We're trying to figure out the probability of yes given E, which means we're saying what is the probability of getting a yes given the evidence. We're also calculating the probability of no given E, which means the probability of getting a no given the evidence. And whichever is greater, if I find the probability of yes given the evidence to be higher or greater than probability of no given the evidence, I say play will be equal to yes. That's the approach. All right. So let's go step by step. So we'll start defining some basic definitions. Follow this very carefully, folks. Extremely important. So we're defining E as intersection of E1, E2, E3, E4. Not very difficult to understand, right? Basically, what I was saying, E is the whole thing combined. Outlook equal to sunny and temperature equal to cool and humidity equal to high and windy equal to true. That's E. We're just separating that into E1, E2, E3, E4. Okay. So E1 is value of the attribute outlook. E2 is value of the attribute temperature. E3 is value of the attribute humidity. E4 is value of the attribute windy. Okay. Now look at this statement, folks. Let's assume E1, E2, E3, E4 are conditionally independent on the play attribute. Okay. Now, what I'm going to do now is I'm going to ask a question. So let's say probability of E1, E2, E3, E4 conditional on play is equal to yes. I've already told you that these E1, E2, E3, E4 are conditionally independent on the play attribute. Okay. So can somebody tell me, I can write this as if conditional independence holds good, how can I write this? Should you want to know? Here we go. Look at this, folks. Look at the last line here. The definition of conditional independence. P of AB given E is equal to P of A given E into P of B given E. All right. Keep that in mind. And can somebody tell me?
Probability of E1 given play.
Okay, E1 given
Play
play
equal to
is equal to yes. All right.
into
Into probability of
E2 given play equal to yes.
okay, play is equal to yes
And
multiplied by
E3
probability
given
of
play
okay,
E3
E3 given play is
play
equal to
yes.
yes. And finally,
Multiplied by
probability of
E4
E4
given play equal to yes.
that's right. Basically, I've done nothing special here, just expanded this. Here there was just A, B. Here you have 4, E1, E2, E3, E4. Otherwise, there's no change in the way conditional independence works. So you're right. So let's go back to this presentation. Now, what do we want? We'll start with this. Probability of yes given E. Okay. So here we go. Probability of play is equal to yes given E. Okay. Now, wait a minute. Am I wrong here? I think there's something wrong here. Wait. What is wrong here? Tell me, folks. There's something wrong here. Is it right?
Is the probability of E should be in multiply?
Wait, one moment. Give me a moment. So what do we need? Probability of yes given E. Okay, wait a minute. I think I've committed a mistake. So A given B is B given A. I think I'm
Into
right. Nothing right. This is right, right? What is this? How did I get this expression? Can somebody tell me? Okay, let's do the simple Bayes theorem, okay? P of A given B is equal to, if I apply Bayes theorem, what will that be equal to? Okay, let's do the
P
basic
of
stuff. Can
B
we say it's
given
P
A.
of AB by P of E? Do we agree? I think this is, I'm sorry, P of B. I think we agree, right? No doubts there. Is that right? This is how,
Yes.
this is conditional definition, conditional probability, right? Correct? Can't I write P of AB as P of B given A multiplied by P of, wait a minute, give me a moment, folks. That's right. So what I missed was, I missed one thing, which is, can you tell me what did I miss here? Can somebody tell me what is wrong with this expression?
multiplied by probability of play is equal to S.
Correct. That is right. That is what I missed. Multiplied by probability of play is equal to, yes. It doesn't alter anything much, but still it's wrong. So let me just add this. Okay, let's do this again. Okay. So we know Bayes theorem. So here's Bayes theorem. Probability of being given A into P of A divided by P of B. That's your Bayes theorem, right? So we have basically, when you have A given B, you can write it as B given A into P of A by P of B, all right? Now what do we need? We need probability of, I'm not going to use the word play for convenience, given E. Now can somebody, not Abhinav, but someone else, write this in Bayes, in Bayes terms? Apply Bayes theorem. So what this would be? If I were to apply Bayes theorem, how would this look? Just apply simple Bayes theorem, folks. Don't expand E into E1, E2, E3, E4. We'll come to that a little later, but just apply Bayes theorem on this.
Probability of S intersection E divided by probability of E.
Sorry, say that again. Probability of?
Play is equal to S intersection E.
Forget play.
Yeah. S intersection E.
Okay, but that's not Bayes theorem. You've actually done conditional probability, okay?
Mhm.
Divided by probability of
E.
E, okay? Then convert this numerator.
Mm. Probability of
How can I write that? Can I write that
E
as E given
intersection S.
E given
Okay,
yes
E given S into
multiplied?
probability of S.
Yes, correct.
Yes.
Divided by
Divided by
probability
probability
of
of E.
E. I don't know why this. Okay. Now, okay. Now what I'm going to do is I'm going to split E as, let's just focus on this bit, okay? Probability of E given yes. Can't I write it as E1, E1, E2, E3 E4 given yes. Can I do that? Because I know E is an event, which is nothing but a concatenation of E1, E2, E3, E4, right? And we know E1, E2, E3, E4 are conditionally independent on this attribute, the play attribute, correct? If that is the case, how can I write this expression? Can I write this as anyone? Someone?
Probability of E1 given yes into probability of E2 given yes into probability of E3 given
That's
yes.
right, correct, right? Basically this expression here, right? Forget the play, but yes, I mean, basically E1 given yes, E2 given yes, E3 given yes, E4 given yes. So if you look at the model here, that's what we've done. E1 given yes, E2 given yes, E3 given yes, E4 given yes. Let me put some brackets so that there's no scope for any confusion. Okay. Divided by P of E multiplied by P of play equal to yes. That comes from here. Okay, this stuff here. That's here. Or let me just put it this way so that I'll put this way so that it's easy to understand. Probability of E. Likewise, I'll put it this way. I'm doing exactly the same thing for no as well. Okay. Just as I calculated it for yes, it's exactly the same way to calculate this for no. Okay, divided by P of E. Again. All right. Now, can somebody tell me, is there a way? I don't want Abhinav to answer. I don't want Madhumita to answer, somebody else. Is there a way to write P of E? This is there in the denominator, right? You see, okay, if you look at what we need to do, let's go back to the objective. We need to calculate P of yes given E and P of no given E. Yes given E, no given E, and figure out which one is greater, okay? So there is a P of E in both cases. In both expressions, we have P of E in the denominator. Can somebody tell me, if I have to calculate P of E, is there a way to condition it on play? How do I do that? Use the law of total probability, folks. So my question is, I have E. I want to condition it on the attribute play, okay, which takes a value of play is equal to yes and play is equal to no. Only two values it can take, right? How do I condition it?
Probability of E given yes.
No, I'm saying condition, right?
Okay.
Start with expressing the set E as some union and intersection of E and play. How do we do that? That's how you start, right? First, you need something which covers the sample space. Don't you see play is equal to yes and play equal to no will cover the sample space? Would you agree? Because there are only two possible cases there, right? So can we write E as E intersection yes union E intersection no? Can we do that? Why? Because we know yes and no covers the entire sample space. There's no other value that it can take. It can take only two values. So I can write E as E intersection yes union E intersection no. Now, can someone tell me, are these two events, this event and this event, are they mutually exclusive? E intersection yes and E intersection no?
Yes, Vijay.
They have
Yeah,
to be. They have to be, correct?
obviously.
So which means, can't I say P of E is P of E intersection play is equal to yes, correct? Plus can we say that? We can, right? I'm going to expand this a little bit more. The way I'm going to expand this is I'm going to write this as P of yes given E multiplied by P of E and can I write this as P of no given E multiplied by P of, sorry, not P of E. Give me a moment.
I have a doubt or a bit confusion. For how would it be an intersection? For example, the set of events given the place equal to yes. We are only conditioning if the yes there is some set of events, if it is no there is another some set of events, right?
I
So
don't
how,
understand. Say that again.
okay, we should have, actually what I am saying is, here is the total probability is P of E given yes plus P of E given no, because for yes there will be some set of events and for no there will be another set of events. So adding the both we will get the complete set, right?
No, I didn't understand. Say that again.
Okay, let me put it this way. So we would arrive at play for some conditions for a particular temperature and climate, and we will arrive at no for some other temperature or windy conditions. So combining that both different, we will arrive at the complete set, right?
So
Am I getting it wrong? I'm not sure.
I didn't understand.
See, see, if, for windy, for we would play if the condition is sunny, and we would not play if the condition is rainy. So like that we would be conditioned based on yes and no only, right? The events are conditioned based on yes and no only.
I still didn't understand.
Okay,
What does it mean? I don't understand.
for yes there will be some set of conditions, right?
Why
For
are you talking about
temperature,
conditions? I don't
because
even know
that's
what those
how,
conditions are.
okay, because
I
that's how we arrive at total probability, I thought.
okay, wait. Isn't this a set? Each one of them is a, this whole thing is like a sample space, right? Correct?
Yeah, right.
Does a sample space, how many points are there in the sample space?
14.
14 points. Now, don't you see play is equal to yes and ploy equal to no will cover the entire sample space?
Yeah, yes.
Now ask your question. This is E, by the way. This is E, correct?
Yeah,
Outlook,
that.
a combination of outlook, temperature, humidity, and windy is E.
Yes, we see.
Okay, now tell me, what's your
So
question?
what I was trying to say is, we would arrive at some conditions for given
No,
place equal
don't
to
use the
yes.
word condition. What condition are you talking about?
For example, overcast, hot, high.
We don't
and fall.
care. Why do we care? I don't know. Why do we
Okay.
even care?
Okay, that's not it works. Okay,
No,
I got
no.
it.
How does it matter? That's my question. How does it
Because that
matter?
these conditions don't influence the play
It
attribute.
may influence, it may not influence. Why are we bothered? That's my question. In this context, why are we bothered? That's my question. When I'm
Oh,
defining E as E intersection yes, union E intersection no, right? E is some E, correct?
yeah, yes,
It's a combination of those 4 attribute values, correct?
yes.
I'm just defining it as E intersection yes, union E intersection no. So let's do this. Let us say E, just say hypothetically, it's not even one row. Let's say it's the first 3 rows. Okay, let's say E is the first 3 rows itself, without, of course, play. Now, can you tell me what is E intersection yes? Isn't it the third row?
Yes. Okay.
What is E intersection no?
The remaining 2 rows.
Now, what is the union of these 2 rows?
Yeah, got it, VC. So
That's
total
it.
set.
That's it. Nothing else.
Okay.
Did we even care that this attribute value is influencing play? Did we?
No.
In my argument, I didn't even bring that into the argument, isn't it? This
Yes,
is
VC.
pure set theory, Abhinav. It's all basic set theory. Nothing to do with probabilities here. Nothing to do with this influencing the other, right? This is pure set theory. Did you get that?
Yes, VC. Got it.
Wonderful.
carry on.
Okay. All right. So here, let's go ahead now. So what I want to write this as, okay, I wrote it the wrong way. Let's write this as P of E given yes multiplied by P of yes. And this is P of E given no multiplied by P of no. Can somebody tell me how did I get this from this? Abhinav, take a shot. How did I get this from this?
So basic conditional probability stuff, right?
Okay, so
Probability of A intersection B, probability of A given B into probability of B.
okay, that's right. Okay, so probability of AB is equal to A given B multiplied by probability of B. So basic conditional probability stuff. Okay, fantastic. Now, let me ask a question. See, the objective here is to figure out probability of play equal to yes given E and probability of play equal to no given E and find out which one is the greater, either this is greater or that is greater, correct? Do we need to calculate probability of E? If I have to figure this out? Because I just need to figure out which one is greater. My question is, do we need to calculate probability of E?
No, we see.
Why?
We just figured out the probability of E is the sum of those conditional probabilities multiplied by the condition.
Even, can you come up with a simpler argument?
But
Look at these two expressions. And then remember the objective. The objective is to find out which one is greater, right? We want to figure out whether probability of play equal to yes given E is greater than probability of play equal to no given E. Now, my question is, to do that, do I actually need to calculate probability of E?
no, we see.
Okay, why? Look at these expressions and tell me.
Yeah, you just now derived the value of P of E in the
No,
Excel.
don't worry about it. Let's say I'm not doing any of those.
No, we are having probability of E1 given yes. So
And
using this,
just have a
we can
look at this
substitute it.
expression, folks. Just open your eyes and look at this expression. You don't need conditional probability. This is like class 7 mathematics. Look at it and tell me.
You can get the ratio from this. Is that what you mean?
Sorry?
You can get the ratio and you can just compare which is greater. Is that what you mean?
Do I need to get the ratio? That's my question.
You can just cancel this out.
What will get cancelled? Okay, let me ask a simple question. Seven divided by 8. 11 divided by 8. Which one is greater?
7 divided by 8.
How did you figure out? Did you do a calculation?
No,
What did you do?
the denominators are same. So
Exactly.
what matters is the numerator.
Exactly. Now look at this. Look at both expressions. This expression and this expression. What's the difference? Don't you see that the denominator is the same? P of E is the same in both cases, right?
Yes, we see.
So for all practical purposes, we don't need to figure out P of E. That's my point. Okay. It's nice to have. Should you want to calculate probability of play is equal to S given E precisely, then yes, we need to calculate P of E. But should you just want to figure out which one is greater? Because that's what we want from a classification perspective. We don't care about the exact probabilities. All right. We just want to know whether P of play equal to yes given E is greater than P of play equal to no given E. So just figure out which one is greater. That's sufficient. So essentially, we just need to figure out the numerator. Just forget the denominator. Okay. Though that is what we need to do in practice. From a calculation standpoint and in the interest of completeness, we will do the calculation. Okay. Now we're going to figure out all these lovely probabilities. Okay. No rocket science. It's simple. You have to stay with me. First thing, probability of play is equal to yes. I say it is 9 by 14. Why?
9 out of 14 samples have yes as the
Exactly,
value.
correct. And probability of play equal to no is 5 by 14. That's evident, right? If 9 is yes, 5 is no. Let's do this now. We'll just do it for one. Conditional on play is equal to yes. I say probability of outlook equal to sunny. Conditional on play equal to yes is equal to 2 by 9. Why?
Out of 9 samples, 2 of them have
What is
outlook.
9? Where did you get the 9 from?
9 samples of yes
Okay.
out of play.
Mhm.
Out of those 9 samples, we have 2 samples having outlook equal to sunny.
Okay, good. Now, sorry, one moment. This should be no. Copy paste error. Sloppy work. Sorry. This should be no. This should be no. And this should be no. Okay, let's pick one of these and see. Now, somebody other than Mukundan, can somebody tell me how we managed to get this? I think I'm wrong here. Wait, it should not be 9. It should not be 9, correct?
5.
Yeah, exactly. Let's fix this column step by step. Okay. Let's start with this. Outlook equal to sunny, play equal to no. So denominator is 5. Easy. Outlook equal to sunny. How many?
3 by 5.
3 by 5. Correct. That's right. Then let's fix this. Again, this is 5. Temperature is equal to cool.
1 by 5.
1 by 5. Okay. Then this humidity is equal to high?
4/5.
Is it 4? Oh, wait a minute. 4/5, is it? No,
Yeah.
no, no.
No.
Okay. Wait, I'm just, no. I'm just reading the nose. 3, yeah, correct. I think you're right. 4/5. Folks, just check, okay? If you're getting it wrong, please do tell us. Okay. Windy equal to true? 3/5. Correct. I think this one is right. Okay. I hope, folks, you got this. All right. Let me just copy this table. I think I would have used this again. I should decrease the font. Give me a moment. Okay. So here you go. So what are we going to do now? So we're going to calculate the end result. Of course, the easy thing to do is don't calculate P of E. Just take the numerator and then I think I'll have to, yeah, I think this one is correct. I put this correctly. Probability of E1, E2. What I missed is multiplied by probability of play is equal to, yes, this is something that I missed here. Multiplied by probability of play is equal to no. Okay. All right. So what are we going to do here? It's quite simple. You already have everything in place. So if you take this expression, probability of play is equal to yes given E. You've already derived this expression before. E1 given yes, E2 given yes, E3 given yes, E4 given yes, into probability of play equal to yes divided by probability of E. Likewise, probability of play given play equal to no given E is E1 given no, E2 given no, E3 given no, E4 given no, multiplied by probability of play equal to no divided by probability of E. All right. Now, should you want to derive probability of E, not too difficult, you can use this to figure out the probability. Now, don't you see this whole expression plus this expression? Isn't that P of E? Do you see that? Look at this expression, folks. Look at this expression. I'm just highlighting it. And look at this expression. Don't you see that the sum of these two is equal to probability of E, right? You would find that. Now, of course, in our world, we don't need probability of E, but should you want to figure it out, you can do that, okay? So if you do the math, you multiply all these numbers with whatever you have here. What you would get is, in this case, I'm actually calculating the probability. You don't need to do that. You just need to multiply the numbers in the numerator. That's sufficient. You'll find that this is equal to this number, 0.0053 by 0.0053 plus 0.0206. And this probability, where probability of play equal to no given E would be 0.0206 divided by 0.0053 plus 0.0206. So this is like 20.5% and this is 79.5%. And since this is greater than the other, this is classified as no. This recorded instance is classified as play is equal to no. Okay. Let me ask a question. The question is as follows. Of course, this is a completely different method towards calculating or rather figuring out the classification. Our first question would be, what is the most fundamental pitfall of doing this? So let's say you give me this record, okay? Outlook equal to sunny, temperature equal to cool, humidity equal to high, windy equal to true. And I tell you, play is equal to no. What's the most fundamental pitfall? When I say pitfall, not from a calculation perspective, but from a very different perspective. I'm not going to say what it is, but I want you guys to think about it. What's the most fundamental pitfall there? Not from a calculation. Calculation may be perfectly fine. It may predict things perfectly fine. But there's something fundamentally not wrong, but it's not a fallacy, I would say, but it's a pitfall.
The outcomes are dependent on the like data set. If it is one-sided, that is.
But
if
that's true
there
for
is-
any tree that you would. I mean, even if you were to use decision trees to construct this, it is dependent on the data set, right?
Yes.
So why would you call this as a pitfall as compared to what we do with decision trees?
I'm not sure, but if there are no instances of no, the answer would be surely yes. That is, it is dependent on majority ones. I think
There's a more mundane reason. Think about it, folks. There's a more mundane reason. Okay, let me put it this way. I'm going to give it a. I'm going to throw it. I'm going to rephrase this problem a little differently. Let's say this is not data related to playing tennis, but let's say this is related to deciding whether to offer a credit card to an individual or not. So you have stuff like, say, salary, you have age, you have, say, educational qualifications, so on and so forth. And then the last column is to give credit or not to give credit. Okay. Whether to give a loan or not to give a loan. Now, in that context, I'm giving you some values for salary and then for age and then for educational qualification. And then the algorithm says, no, don't give him a loan. Would you be happy?
No,
Why?
because I am supposed to get a loan.
Well, that's just your view. But how? That's just your view. But when I say, would you be happy? What I meant is, what would you expect? I know. Or let's say, forget. Okay, let me put it this way. I'm an employee of State Bank of India, and you do this. You run this algorithm, and I say, look, Abhinav has to get this loan. What is wrong with you? How can your algorithm say it is no? How would you justify it? Let's say you run this algorithm, and then it says Abhinav shouldn't get credit. It says no. But I'm an employee of State Bank of India, the same bank where we work. I mean, somebody is running this algorithm in the bank and he or she also works with me. I ask her, look, my gut feel says Abhinav should get this loan. What's wrong? Something is fundamentally wrong with your algorithm. Let's say I say that. How would you respond? Is there a way to respond to that?
We have to work on the metrics of that algorithm, precision, recall,
Okay,
F1 score.
I don't even know machine learning. I'm a branch manager. Imagine you guys have seen branch managers, right? You would have seen branch managers in your colleges. You go to SBI, there'll be a manager sitting there. You think they'll understand precision, recall? They're not going to understand any of those. How do you explain? Is there a way to explain?
No.
No. In one of those previous algorithms that we worked with, was there a way to explain? Which algorithm would help you to explain things to this manager who doesn't understand machine learning?
Maybe some other simpler
Okay, which algorithm? We've done that before. Which algorithm?
linear regression.
Linear
Sorry,
regression. You think
logistic regression.
you think so you strongly believe that a manager at State Bank of India will understand linear regression or logistic regression?
The exam is supposed to be.
Sorry,
Maybe they may not.
they won't. So which algorithm is easy to?
Say 4.5 algorithm, we can build the decision tree and they can understand it intuitively
Absolutely correct.
where the instances goes. But here
Exactly.
after the with the computation answer, you can say
Exactly. So if you take the decision trees, right, it clearly says if outlook is equal to sunny, then do this, right? So anybody can understand that. So if Abhinav doesn't get credit, and if I ask some of these guys who built the algorithm a question, how the hell did you build this algorithm? I say it's wrong. Then with a decision tree, you can explain. This is the reason why Abhinav didn't get credit, because this is what the algorithm does. It divides this into a bunch of rules. You can call that as a simple decision tree. People understand basic decision trees. So it's not very difficult to understand, right? And the reason why I'm saying that is if you go back to the Telegram group, I don't know how many of you followed it, but let me just bring it up. Give me a moment. Can you see the group? I hope you can. Can you see Telegram, folks? I hope you can.
Yes, please.
All right. Okay. Now, look at this. A major obstacle in the adoption of complex machine learning models. It's called black box models. So the one that we built now is essentially a black box model, right? You don't even know what's happening inside the box. For credit risk models, okay, don't get confused. Credit risk models basically means whether to give a loan or not. A model that will help people to figure out whether to give a loan or not. Is compliance with regulations, which means, let me explain. More specifically in the United States, the Fair Credit Reporting Act of 1970 requires that if an applicant is denied credit, the lender must be able to explain the reason for the decision. So if Abhinav doesn't get credit, the law of United States says that Abhinav should be explained why he was denied credit, right? Now, if you use one of these complex, fancy algorithms, nothing fancy about what we did now, it's simple. In fact, it's called naive Bayes because it's very simple Bayes. It uses simple Bayes theorem. So it's called naive Bayes, the one that we did. But still, it's still a probabilistic model. So with probabilistic models, it's very difficult to explain in this particular context the reason why credit was not given. All right. Now, which is why, so if you look at, I'll just show you one thing. Sorry, give me one moment, folks. Sorry. What's wrong? Did I get it wrong? Maybe I should do this way, is it? I think it's right. All right. So this guy has been working on credit risk modeling for 1.5 decades. Look at, he says he's an expert in decision trees. You see that? So the reason why decision trees matters to him is because, of course, he knows logistic regression too, but he says he extensively uses decision trees because he is bound by regulation, which in most markets, Western markets, see in India, nobody cares. உனக்கெல்லாம் லோன் கிடையாதுயா போயா அப்படின்னு சொன்னா நம்ம போயிடுவோம். இந்தியாவில் அவ்வளவுதான். இப்போ யூஎஸ்லாம் போனீங்கன்னா ஏன் லோன் கிடையாதுன்னு சொல்லு அப்படின்னு கேட்கலாம். The law permits you to ask that question. And when the law permits you to ask that question, you need a proper answer. You can't give them probabilities and say P of E given A, Bayes theorem. You can't give all that answer. You'll have to be very, very clear, which is where decision trees are much more useful. All right. Now, this actually comes back to, again comes back to the utility of these machine learning models. The more complex it gets, it's fun from a mathematical standpoint. But the question is, can you sell this algorithm to those who don't understand the mathematics, right? Which is why it's extremely important that as data scientists, you need to have the ability to tell a what? Tell a what? You need to have the ability to tell a, take a guess.
Story.
Absolutely. Storytelling is absolutely important for data scientists because you can do all the mathematics. Nobody's going to understand the math. They would trust you because you've done engineering, you've done a lot of mathematics. They will trust you. They'll trust your experience. But what's very important is the story. If you get the story right, if you get it very convincing, they'll believe your math. You get the story wrong, they're not going to believe your math. So remember, folks, which is why I keep insisting that write a lot, because that's the only way to improve your storytelling skills. Okay. Anyways, so going back, that was one problem. We'll just look at one more problem, and then we'll stop at that. Now look at this, folks. Look at this formula. E1 given yes, E2 given yes, E3 given yes, E4 given yes, so on and so forth. And we multiply all of them, right? There's one more problem with taking this approach. What is that? Given that we are, I'm going to give a clue. Since we are multiplying all these probabilities, okay, since we are multiplying all these probabilities and you know how these probabilities are calculated, there's one more problem. What is it?
Here we assume that all the attributes are conditionally independent.
Okay, that's a assumption. Let's say that's okay. More than that, anything more than that? Okay, let me ask a question. Let's take this probability of outlook equal to sunny given play is equal to yes, right? Let us say for some reason the data set does not have, it has the record sunny, okay? It has the record sunny. Okay, let's take this case. Temperature is equal to cool, where play equal to no. Okay, let's take this case. We were cutting so close there. What would have happened had there been no record where temperature is equal to cool when play is equal to no? What would have been this probability? Can someone tell me? What would have been this probability?
0.
0. So if that's 0, what would have happened to that product?
0.
0. Correct? So don't you see how sensitive we are to the kind of data that is needed to compute, these probabilities, right? If for some reason you don't get this data in the data set, then it's almost impossible to run this algorithm. Now, there are ways to solve that problem. We will discuss that later. But that's the second problem that we face with this algorithm. Okay. So now this whole algorithm is called as naive Bayes. The word naive means simple. We're using basic simple Bayes theorem to figure out the the classification. And going back to what I sent today, so these two characters, James Madison, Alexander Hamilton, they wrote a bunch of letters way back in the 17th century. Out of them, 12 letters were such that nobody was sure about the authorship of those letters. There were totally a lot of letters, by the way. Many of them were attributed to either James Madison or Alexander Hamilton. 12 letters couldn't be mapped to any of these authors. So that remained a mystery for long. 1960, somebody sat and used Bayes' theorem to figure out who actually wrote the letter, whether it was Madison or Hamilton. So way that was done was basically they took all the letters that Madison wrote, they took all the letters that Hamilton wrote, and then so each person has their own style, right? This is not the world of ChatGPT. So each one would have their own style. So depending on the writing style, which words they use frequently, they managed to figure out the authorship of the 12 letters. All right. I'll finish our session today by reading a portion from a text. Give me a moment. I'm going to read a portion from this text. (103). Sorry. Apologies, folks. I don't know how to. I think I can do this. Yep. Sorry, let me just enable scrolling. Yep. Read this. This is very instructive. It says, naive Bayes gives a simple approach with clear semantics to representing, using, and learning probabilistic knowledge. It can achieve impressive results. People often find that naive Bayes rivals and indeed outperforms more sophisticated classifiers on many data sets. The moral is always try the simple things first. Over and over again, people have eventually, after an extended struggle, managed to obtain good results using sophisticated learning schemes, only to discover later that simple methods such as forget IR, simple methods such as naive Bayes do just as well or even better. All right. So remember, folks, doing something extremely complex, it doesn't mean that it's right. Okay. You can have a very complex algorithm that nobody understands, but that doesn't mean that you're right. Does anybody know? I'll just stop with that because we'll have a hard stop at 12. Does anybody know that I'm trivializing it? So in 2008, there was a big economic crisis, much worse than what you're seeing now. It was one of the biggest economic crises that we witnessed since the 1930s. You know who caused it? Who were behind the economic crisis of 2008? Can you take a guess? Take a guess. Don't Google, folks. You're not going to get that answer so easily on
Was
Google.
it a bank?
It's more simple and mundane. Let me give an answer. It's physicists and mathematicians. They were responsible for the crisis. So you know what happened? So way back in the 80s, 70s, and 60s, and 80s. So the era of physics ended in the 1960s. Beyond that, there was no scope for physics. Still today, there's absolutely zero scope for physics. So all those folks who joined a PhD program in the 60s, 70s, and maybe even 80s, they joined the program assuming that they'll do some great work in the world of physics. By the time they completed their PhD, they knew that nothing is going to go forward in the world of physics. They can't even become a lecturer. Forget, you could do a PhD at Princeton, but still you won't even find a lecturer's job in the US. You'll probably go as a school teacher. So bad was the situation. It continues to remain bad, by the way. So where did these guys end up? All these physicists and mathematicians, they all ended up in the world of finance. So what they did was all that knowledge. So finance was getting much more mathematical those days. Okay. Earlier it was very simple. It became very, very mathematical. So what these guys did was they brought in all their knowledge of physics, because physics involves a lot of modeling, a lot of statistics too. So they brought in all that knowledge to the world of finance and did some really, really complex stuff to the extent that nobody understood what was happening. Okay. I'll probably send something in the group so that you understand. So there was a very short movie taken on this particular aspect, where a nuclear physicist joins a Wall Street firm, and you'll understand what I'm talking about when you watch that. It's a brilliant movie. It's a short movie. I'll share it in the group. So so these guys, they joined all these Wall Street firms, did complex modeling that nobody understood. Everybody thought it works because these guys said so. it just so seems that in their modeling, they assumed, in most of the models, they assume that the returns follow what is called as a normal distribution. Apparently, during 2008, the actual data was not quite normal. It just moved. It became skewed. And all their models crashed. Nothing worked. All these big Wall Street firms went into deep losses. The world went into an economic crisis. And then they had to pump, the Federal Reserve had to pump billions and billions of dollars, free money, literally free money. Note adichu kuttanga, literally, to make sure that the economy survives. So if you think of the root cause behind all this, it goes to the physicists and mathematicians who brought in complex algorithms into the world of finance. And the reason why I'm saying this is because just because a model is complex, it doesn't mean that it has to be good. Okay. That's a very important learning for us. But of course, we have to clear interviews too. That's a very important objective. And எவனாவது சைக்கோ உட்காந்துருப்பான் என்ன மாதிரி அவன் ஏதாவது கேள்வி கேட்பான் அதுக்காக it's good to know complex algorithms, but in practice, should you ever choose to become a data scientist, or if you end up being one, always keep this in mind. Keep it simple, keep it stupid, and make sure that you have a nice story to tell. That's what, from whatever little that I've heard, much of data science is about telling nice stories. Okay. Any questions? All right. If there aren't any, we'll stop for the day. Thank you, folks. We'll meet on Friday.
Good night, Rishi.
Good night.